This is problem 19 from chapter 18. The rotary screen S is used to wash limestone. When empty, it has a mass of 800 kilograms and a radius of gyration of 1.75 meters. Rotation is achieved by applying a torque of 280 Newton meters about the drive wheel at A. If no slipping occurs at A and the supporting wheel at B is free to roll, determine the angular velocity of the screen after it has rotated 5 revolutions. Neglect the mass of A and B. So we're going to use the work energy conservation law, and that is equation 1818. The center of mass for the screen is not changing, so there's no change in gravitational potential energy, so we can say T1 plus the sum of all the work is equal to T2. Assuming that the screen is starting from rest, T1 is equal to 0. Since the mass center is not moving, the 1/2 mv squared, where v is the speed of the mass center, is equal to 0. So the kinetic energy is 1/2 times the moment of inertia about the mass center times omega squared. They gave us the radius of gyration. The moment of inertia, if we're given the radius of gyration, is m times k squared. So I can say T2 is equal to 1/2 mk squared times omega squared. Now I have to find the work done, and I can use equation 1812. I can put in the 280 Newton meters, integrate with respect to theta, and that just gives me 280 times delta theta. But this was the torque about the drive wheel at A, so this change in angular position is for A, and I have the change in angular position for the screen, so I want to relate those two, but the change in position, delta S, is the same for A and for S. So you could say delta S is equal to, the radius here is 2 meters, so that's 2 times the change in angular position for S. The radius of A is 0.3 meters, so that's equal to 0.3 times the change in angular position for A. So I can say delta theta A is equal to 2 divided by 0.3 times delta theta S. So I have the work done is equal to 280 times 2 divided by 0.3, and then the change in angular position for the screen is 5 times 2 times pi. Let's call that 10 pi. Okay, now I can go back to my work energy relationship here, and I have T1 is equal to 0. My work is equal to 280 times 2 divided by 0.3 times 10 times pi, and that's equal to T2, which is 1/2 times the mass, which is 800, times the radius of gyration squared, which is 1.75 squared, times omega squared. And then we can solve for omega, and you can do that, and you should get 6.92 radians per second for your answer. And that concludes problem 19.